Hello, everyone. Today's speaker is Dr. Shi-Hao Li. His title is Condensation Algorithm for Pfaffian and Discrete Integrable Lattice. So please start.
Yes, okay. Thanks for the organizer's invitation for me to give a talk here, and also thanks for everyone's coming. And I'm Shi-Hao Li from the Sichuan University. And before I joined the Sichuan University, I was a postdoc at the University of Melbourne. So I think I have many connections with the Australian integrable system community. And it's a great honor of me to give a talk today. And here it's a title of the title of my talk is the condensation algorithm for Pfaffians and discrete integrable systems. So firstly, I will give you some content of today's talk. Firstly, I will give you some introduction about the condensation algorithm for Pfaffia and some motivations of this talk. And then I will give you the first condensation algorithm for Pfaffia, and this one is motivated or comes from the computation algorithm for some Vapia sequence transformation. And after that, I will give you another condensation algorithm for Pfaffia, which is related to the discrete BKP equation. And finally, I will give you some conclusion and remarks about this talk. And this talk is based on my preprint entitled The Discrete Integrable Systems and Condensation Algorithm for Pfaffia, put on the archive last year. Firstly, I will give you some brief introduction or motivation of this talk. So in 1966, Dawkinson proposed a condensation algorithm of determinant. And here I will give you why it is called the condensation of determinant. So if a matrix is given, n times the matrix A is given with the elements Aij, and how we use the condensation algorithm to compute a determinant of the matrix A, and here are the steps. Firstly, we will use the inventory row and the column operations to remove all zeros from the interior of A, and then we find the 2 times 2 determinant for every 4 adjacent terms to form a new n-1 times n-1 matrix B. I will firstly give you the introduction of the steps, and then I will show you an example. So don't be worried, I will give you an example later. So after we get B, and we repeat this state to produce n-2 times n-2 matrix, and then divided the interior of A to obtain C. And we repeat this process, and then we can continue condensing the matrix until a single number is obtained, and this single number is the determinant of A. So here is the example. I give you the matrix A, which is actually given in this 4 times 4 matrix, and then if we compute every 2 times 2 adjacent matrix here, this 2 times 2 matrix, the determinant is 14. It is 2 plus 12 is 14, and then we just arrange all of these numbers in a new matrix. We call it B, and then we do it again. To compute every 2 times 2 matrix and obtain a small number, which is in this form. And then we divide this matrix by the interval of A, which is 1, -2, 4, and 2. And then we can get a C. I mean, the C is obtained by dividing this matrix by the integral of A, which is this one. And the determinant of this one is -84. And the integral of B is -6. So we can get the final number is -84 divided -6 is 14. So the determinant of A is 14. So we can say we just follow in the condensation and then get the final number, which is 14. So this is the step of the condensation. So why does it work? So the principle and or the fundamental theory of the condensation algorithm is the Jacobi identity of determinant, or this Jacobi identity of determinant is also called the Discrete-Jacobi adjoint matrix theory, which means if we denote Mij is the matrix M with S row and J's column removed, then we get this kind of determinant identity, which is a bilinear identity. And if we specially chosen the IJKL as the first row, last row, first column, and last column, and we can draw the identity in the following way, which is very easy to remember. Sorry. Okay. If there is no problem, I will continue. Yeah. So if we just choose IJKL as this very special choice, then we can draw this kind of picture, and this one will be used to explain how the Jacobi identity is related to the condensation algorithm of determinant. So if we denote the tau n LM as the determinant of order n, which and the first element is labeled by L and M, and we just denote this kind of determinant as the tau n L and M, and use and we can use the Jacobi identity in this form, right? In this form, and then we can say that tau n LM times the integral of this one is tau n -2 L plus 1 M plus 1 is equal to the first determinant is delete this 9 and this 9, which is the tau n -1 L plus 1 M plus 1, and times this one, which is tau n -1 LM, and minus this one, and this one is this, and this one is the last one. So this is this is this is the Jacobi identity, and we use the Jacobi identity, and we can get this equation, and this equation is the discrete KP equation, or the so-called Herota's difference equation. And this is very famous equation in discrete integrable systems. So a very natural question here is how to realize the Herota's difference equation as the Dawkinson's condensation algorithm. So here it is the relation. So our aim is to compute the tau n 0, which means the determinant of A. I mean, the A is matrix of Aij, and Ij is from 0 to n-1. And our aim is to compute the tau n 0. And the method is to store the tau 0, which means the determinant of order 0 is all stored are all stored by 1, and the tau 1 LM are stored by the elements of the given matrix, I mean the ALM, and then we can use the identity, by which I mean if we take n is equal to 2, then we can compute all values of tau 2 LM. Since if we take n is equal to 2 and this one is 1, I mean tau 0 of all identities are 1. So here it is tau 2 LM, and tau 1 are given by the matrix elements. So we can compute all tau 2, and then we can take n is equal to 3, and then we can compute all of the tau 3, and next we can get all of the tau n, the value of tau n, and finally the determinant of the matrix can be given. So the conclusion is Herota's difference equation, or the so-called fully discrete KP equation, or the three-dimensional Toda equation, or fully discrete Toda equation, can be used to compute the value of determinant. So here is the connection between the discrete integrable system and the condensation algorithm of determinant, or the so-called Dawkinson's condensation algorithm. And here is the graphic explanation of the fully discrete Toda equation, or Herota's difference equation. So I mean we can compute this point of value from the given points of these 5 points. So you can remember that if we give the n is equal to 0 of this plane, and give tau 1 from this plane, and we can compute tau 2 and from this plane, I mean the LM plane, and then follow this procedure, we can compute all of the tau 1, no matter how big the order of matrix is. So this is the graphic explanation of the fully discrete Toda equation. So why this Dawkinson's condensation algorithm is so famous? So why people are interested in Dawkinson's condensation? And one of the reason is it is related to the lambda determinant, which can be given from the Dawkinson's condensation. So here I just follow the notation of DeFrancisco's paper, and here I just use the affine transformation. I just map the index k to the k minus l, and the l is k plus l plus n, and this tau is denoted by capital T here, and then we can get this equation. And this equation is actually equivalent to the fully discrete Toda equation, and these initial values are also equivalent to this one, if we just follow this affine transformation here. So after that, we just replace this minus sign by the plus lambda And then if we iterate this equation by the initial value given here, then we can get the so-called lambda determinant, which is now very famous in combinatorics, which is also related to the alternating sign matrices. And this concept is also related to the 6-vertex model, since the lambda determinant has has some properties, and you can see, okay, the coefficients of the lambda is of some polynomial form, so it has some Laurent property, and also this is also called the T system, and it's related to the cluster algebra and so on. So this is very, very famous in nowadays mathematical physics, and so also the importance of the Dawkinson's condensation is very famous. So if you are interested in this kind of topic, you can find it at the, I think it's famous in DeFrancisco's paper called the integrable combinatorics, which is he gave this talk at the International Congress of Mathematical Physics in 2012. So another application is if we do some no dimensional reduction. I mean, if we take tau nkl as the head tau with all the nkl is connected by the n plus 2k plus 2l, then the head tau satisfy a Somos 4 sequence, which is in this form. The Somos sequence is also a very interesting topic in combinatorics, and in recent years, like Professor Andy Hohen and Shankar Chang and Xinbiao Hu, also they did some works related to the Somos 4 equation or Somos 4 sequence to show their Laurent property, their solution with some initial values to express this tau as some Hankel determinants, and the elements should satisfy some relation with the initial values. And here are some reference related to the Somos sequence and the Dawkinson's condensation. I think it's related to the Dawkinson's condensation. So, okay, so here it is the motivation of this talk. I mean, since the Dawkinson's condensation algorithm is very powerful and useful in modern mathematical physics, so it's very natural for us to ask whether there is any analog of the Pfaffia's version. I mean, the condensation algorithm for Vapia. Since this talk is given in a integrable system seminar, so personally, I will give some very brief introduction of Vapia, since not everyone is very familiar with Vapia. So I think I should give a very brief introduction here. And if we are very interested in this topic, you can find many books or textbooks related to the Pfaffians. So a Pfaffia is given to an anti-symmetric matrix A. So here, given an anti-symmetric matrix A with the skew symmetry Aij is equal to the minus Aj, and then we can define the Pfaffia of A in this form. I mean, the I1, I2 are some pairs, and they should obey the rule I2 L minus 1 is less than I2L plus 1, and also I2L minus 1 is smaller than I2L. So this is the pairs it should satisfy. And in modern mathematical physics, there are many applications of the Pfaffians, like the quantum field theory or the conformal field theory, since the Weik's theorem will give you some bosons into the into pairs, and then they can be expressed by the Pfaffia. And also in Soliton's theory, like the solutions of the B-type equations, like the Savart-Cotera equation or the BKP equation or DKP equation, their solutions can be given by Pfaffia, and you can see from Herota's book, right? So in Soliton's theory, Pfaffia is also very useful. Still, in numerical algorithms, nowadays how to compute the value of Pfaffia is also very hot, it is a very hot topic, since you can use the skew LU decomposition of the skew symmetric matrices, and we can also see some combinatorics topic related to the Pfaffia, which are called the non-intersection paths and the plane partitions. So we can see Pfaffias is a very powerful tool, and it appears in many different subjects in mathematics and physics. And here are some sentences I quoted from the papers or books. So Klaus is a professor of the Stanford University, and he is also the winner of Turing Awards. And in his paper, which called the Overlapping Pfaffias in 1995, he said Pfaffias are more fundamental than determinants, in the sense that determinants are merely the bipartite special case of a general sum over matchings. So in this paper, he considers some combinatoric objects, and he say, okay, Pfaffias are more fundamental. And in Herota's book, he say Pfaffias are usually defined by the property that the square of a Pfaffia is a determinant of an anti-symmetric matrix. But this property often gives rise to the misunderstanding that a Pfaffia is merely a special case of a determinant. In fact, it is more natural to regard a Pfaffia as a generalization of a determinant. So if you are familiar with the bilinear method, you can see that all the determinant identity can be realized as the Pfaffia identity. So Pfaffia, in some sense, or in this case, is more general or more natural to regard Pfaffia as the generalization of a determinant. So it's natural for us to ask whether there is any condensation algorithm of Pfaffia. And here is the first algorithm to compute the value of actually was found maybe 3 to 4 years ago, when we consider a reasonable acceleration for the Pfaffia sequence transformation. And in this paper, we just want to compute some Pfaffia sequence transformation and want to acceleration to find a convergency acceleration algorithm for this Pfaffia sequence transformation. And finally, we found an algorithm which is used to use that acceleration algorithm. And but after that, Professor Hu asked me, can this algorithm can be generalized as a condensation algorithm of Pfaffia? And finally, I found, okay, yes, this one is useful to, it can be used to as a condensation algorithm. So here this is the equation. We can say this equation was given in this oops. I mean, sorry. This equation was given in this paper, and if you are interested in how this equation appear, you can find from that paper. You can refer to that paper. And here is the equation, and the initial value was given in this form. Here, the tau 0 is also given by 1, and the tau 1 is given by all the elements in Pfaffia. Oh, no, tau 1 is just the Pfaffia 0, 1. And they are computed by this form. I mean, the Pfaffia ij 0, 0. I mean, all the elements in Pfaffia are stored by Pfaffia ij 0, 0. And we can also store the label k by a shift of the label in I and j in this form. Also, the label L can be obtained by this kind of form. This is it's actually a discrete dispersion relation of the Pfaffia. So just store the label L in this form, and then we can see from these two equations. Firstly, from the tau 0 and the tau 1 and sigma 0 here, sigma 0, we can compute tau 1 in the first equation. And then if we get the tau 0, tau 1, sigma 0, sigma 1, now we can turn to the second equation, to the tau 2. If we set n is equal to 1 and tau 2 is related to tau 0, sigma 1, tau 1, sigma 1, tau 1, tau 1, tau 1, tau 1, tau 1, and then we can compute the tau 2 from the second equation. And then we can go back to the first equation to get the sigma 2, and then to get the tau 3 from the second equation, and then iterate back and forth. We can finally get the tau n from this equation. So here is an example to explain how this integrable system can be regarded as the algorithm. So if we consider a second order Pfaffia, which is actually denoted by the Pfaffia Aij and Dij from 0 to 3, with Aij is equal to minus Aj, and the initial value is given by tau 0, 0, 0, and tau 0, 1. Sorry, tau 0, 1 is given from this equation, and the tau 1, 0 is from this equation, and tau 0, 1, 1 and tau 0, 2, 0 and this one, all these, sorry, all these label, I mean label switched by K and L are obtained by these two different kinds of dispersion relation. Yes, these two are discrete dispersion relation, and you can also regard that as the initial values. So we can sit in these initial values, and then we can iteration from the first equation to obtain all the sigma 1, and you can compute sigma 1 0 1 is equal to this, and sigma 1 1 is equal to this, and then iteration from the second equation, we can get tau 2 0 0 is equal to this one, and this is the second order Pfaffians expansion from the definition. So of course we can regard it as we regard these two equations as the condensation algorithm of Pfaffia, and its integrability is also given by this paper. And if you are interested in, you can refer to that paper. Yes. And also, I ever wrote a MATLAB program to realize this algorithm. And if you are interested in, you can ask me to send you a MATLAB file and then you can operate it in computer. And besides the condensation algorithm I mentioned just now, here I just want to mention you another condensation algorithm of Pfaffia, which is more natural to think about, since as you can see, these two equations is very complicated, right? Since it has 5 terms in each equation, and it has tau and sigma, so it is a coupled equation. In some sense, I regard it as a discrete DKP equation, but I don't have any evidence to show that it is a discrete DKP equation. But from my perspective, since it is a coupled equation and no end, since it is a coupled equation, and I don't know whether it is of D type or any other type, but anyway, I know the second one is of B type. Yes. So the second condensation algorithm for me is discrete. It is related to the discrete BKP equation, and here I will show you how it is related to the discrete BKP equation. And also the discrete BKP equation is also called the Vivas equation. So I will show you how this equation can be regarded as a condensation algorithm. Actually, indeed, many years ago, some scholars from the combinatorics want to find the condensation algorithm for Pfaffia. Like in this paper, the cube recurrence. These two scholars want to find the condensation algorithm of Pfaffia. Also in this paper, they want to get some lambda Pfaffia from the condensation. They use the Pfaffia identities, but I don't think it is a condensation algorithm, since I will explain it later, since the identities are correct, but if you want to realize this kind of condensation algorithm, you should introduce the odd order Pfaffia. I will explain it later. So here are some previous attempts to the condensation algorithm of Pfaffia. And here this is the cube recurrence appeared in this paper, and it is actually the Vivas difference equation, which was also the title of this paper is called the Herota's difference equation, and sometimes we now call it the Vivas difference equation, or the discrete B-Toda equation, or B-Toda lattice. However, this equation is implicit to iterate, since you can see the right hand side of the n of the nebula n, you need to solve a difference equation about the nebula n. So this equation is implicit to iterate. So we want to find an explicit formula to get the condensation of Pfaffia, and this is the motivation of the second algorithm. So here is a graphic explanation of the previous equation. So you can see these two points should be given from just one equation, and this is very difficult to compute if you just use the computer to solve a first order difference equation. So one can hardly compute the explicit value for the points at the top. So how to realize the condensation algorithm of Pfaffia? Here I'd like to mention the generalized Noether-Vatel equation, or lattice. This lattice was given by us in this paper, and here here we can see the nebula n is explicit to compute, since this is n-1, n+1, n+1, n+1. So if we know the lower floors of the lattices, then we can explicit to compute the highest level of the value of in this equation. And here I'd like to mention also, this equation is the backbone transformation of the B-Toda lattice we showed before, and it can be explicitly iterated. Although we call it as a generalized Noether-Vatel equation, it has no connection with the Noether-Vatel equation because it is of B type, or yes, it is of B type. So, but if we dismiss the discrete variables K or L, then this equation can go back to the fully discrete Noether-Vatel lattice, but it has no connection with the Noether-Vatel lattice. This is not a connection, but why we call it as a generalized Noether-Vatel lattice. Oops. So please don't do any marks on the slides. Thanks. So here it is a graphic explanation of the condensation algorithm of Pfaffia. So we can say this is the square. The lattice of three level of 4 level. We need to if we want to know the value of this point, we need the values from 3 different levels. But this value can be explicitly computed from these 3 different from these 3 levels. So this is a graphic explanation of the generalized Noether-Vatel equation. And here I will show you how I can say that equation can be realized as the condensation algorithm. So firstly, of course, I need some preparation of data or setting the initial value. So just store the elements Aij as the Pfaff ij00, And then here are the discrete dispersion relation related to the label K, and this one is related to the label L. And here also we need two free parameters. These two parameters are very free. You can say here that any value as alpha j, and just denote the di00 as alpha I, and here are some dispersion relations related to this alpha. And then just iterate this equation. How to iterate? We need to split the tau 2n and tau 2n plus 1 separately, and we get two different equations coupled by here I call it phi and psi, and we can compute the psi n from the first equation and the phi n plus 1 from the second equation. I mean, you can see here I just make a very small explanation. So I say one can use the first equation to obtain psi 1. Since you can see if we set n is equal to 1 and psi 1 is given by phi 0, psi 0, phi 1, psi 0, phi 1, psi 0, phi 1, and these are given by the initial values. And if we so we can get the psi 1 from the first equation, and then we can get phi 2 from the second equation, and back and forth we can get the phi n00 from the iteration. So this is the goal of the iteration, and this is the condensation of the Pfaffia. So here is the condensation algorithm of Pfaffia, and we use the the generalized Noether-Vattara equation as the condensation algorithm. And here are some remarks. The first remark is, as you can see here, I just split the equation by 2n and 2n plus 1. And here the tau 2n plus 1 is actually a Pfaffia of odd order. I call it an odd order Pfaffia, which I introduced the new label D0 here, and it is very efficiency in the condensation algorithm. I'd like to tell you that the odd order one is very useful in iteration, since if you just use the even order one, and you can hardly find the condensation algorithm just by using the Pfaffia identity from the even order Pfaffia. You can see from this paper. Okay, you can see from this paper, they just want to use the even order Pfaffia to find a condensation algorithm, but I don't think it's a condensation algorithm. You can't obtain any explicit value from the lower levels. So you should introduce an odd order Pfaffia to find the condensation algorithm. Also, the odd order Pfaffia results in some other subjects, such as the partial skew orthogonality. As you can see from our paper in Communications in Mathematical Physics in 2018, in that article, we introduced the concept called the partial skew orthogonality because of the odd order Pfaffia. Since the skew orthogonal polynomials are all related to the even order Pfaffia, but how the odd order Pfaffia appear in orthogonality. And in that paper, we give an answer to how this kind of Vapia play a role in orthogonality. And also, this one can be explained in Graves-Morris vector Padai approximation. If we think, since this one can be used to iteration, so also it can be used to solve some Padai approximation theory. And the second remark is something related to King and Schiff's work. And here I'd like to thank Professor Andy Hohen. Since in 2019, he visited me at the University of Melbourne, and he just discussed with me about his work about the thermal sequence and the condensation of determinant. And I told him that I found the condensation algorithm of Vapia. So he encouraged me to write this paper down. And so why this paper come after the previous works. So I'd like to thank Professor Andy Hohen to mention me the work of King and Schiff. So he mentioned me that King and Schiff in this paper, they proposed a 14-point scheme of a BKP equation. And I suddenly realized that if we start from the Bitoda equation, with this Bitoda equation, and then consider the background transformation in 3 dimensions, in 3 directions. I mean the NLK in these 3 directions, and in every direction, we just need to add 2 points. Then this 8-point scheme will be extended to a 14-point scheme by considering a discrete BKP equation or Bitoda lattice with 3 different direction spectrum transformation. So I think this one should be related to the work given by King and Schiff in this paper. And this is the second remark. And finally, I will give you some conclusion. So the value of Vapia is very close to the integrable system theory, since if you do some bilinear methods, you know that Vapia is a very powerful tool to get the solution of integrable systems. And we have 2 different ways in the computation of Vapia law. One is based on the group factorization, and the other is based on the condensation. In fact, I did some work about the group factorization of Vapia, since it is related to the skew area decomposition or the skew borrow decomposition. And also since from the skew borrow decomposition, we can obtain some corresponding dressing operators, wave functions, and Knox representation for integrable systems. Here I'd like to mention that Professor Adler and Pierre Van Mobeek did many things about the Vapia tau functions and the so-called Pfaffians hierarchy or something like that. And also some skew orthogonal polynomials can also be obtained from the skew area decomposition. So I did something related to this kind of topics and some topic related to the Pfaffians and so on. And another way to compute the value of Vapia is the condensation algorithm I present here. So the condensation of Pfaffia directly proves some discrete integrable systems and some possibility in connection with combinatorics. And here are some related works about the Pfaffia and the skew orthogonal polynomials and integrable systems. And here, the first part is some skew orthogonal polynomials and integrable systems. Here are two papers, which the first one is about the partial skew orthogonal polynomials, and the second one is Christopher transformations for partial skew and skew orthogonal polynomials. And the second one is about the second topic is about the classical skew orthogonal polynomials and random matrices. This one is this work are mainly collaborated with Professor Peter Forrester, and here are two papers related to the classical skew orthogonal polynomials and random matrices. And this is the end of my talk. Thanks.
Thank you very much. So is there any question or comment? Please raise your hand or unmute and please speak.
Shi-Hao.
Hello.
Hello, hi. I have a question. So,
Okay.
and you're based on the algorithm to compute the determinant, and
Yes.
then you're using the B-column transform of the B toda.
Yes.
You came up with an algorithm to calculate the Pfaffian, right?
Yes.
Explicitly without solving the system.
Yes.
Okay. Yeah, my question that, as you mentioned, the Pfaffian is more general than the determinant. So
Yes.
have you tried using your algorithm and you interpret the determinant as a special Pfaffian and to recover the classical algorithm using and compare these two? Do you understand
Yes.
what I
Yes.
mean here?
I got your question. Yes.
Mm-hmm.
And in this paper, in class paper, overlapping Pfaffia, he considers some Pfaffia and he say, okay, determinant identities can be obtained from the Pfaffias. In this paper, you can see that he says that Pfaffia, from Pfaffia's identity, you can recover the determinant's identity. We also know that from the Herota's book, we know how the Jacobi identity or the Pnuker relation can be obtained from the Pfaffia's identity. But I never tried whether we can use the Pfaffia identity to go back to the condensation of determinants. I think if we use the Pfaffia to understand the determinant, then we will go back to the condensation of determinant rather than the Pfaffia. I think if we apply the Pfaffia identity to determinants, then we go back to this equation again.
Okay.
Yes.
Maybe can I ask you another quick question? I'm sorry, maybe there are some other questions. So in this one, your purpose, your motivation is to calculate the determinant or the Pfaffian. So you increase n, and n is basically the size of the determinant or the Pfaffian, right?
Yes. Yes.
Yeah. Okay. But also I have another, for the same discrete integrable system, I have another point of view. For the fully discrete one, you have n, you have k, you have l. So
yes.
like the total lattice, the k is like the discrete index for the space variable, and the l is the time variable.
Yes.
So you may come up with another question that you wanted to using that algorithm to numerically compute the discretized solitary equation. So basically, like a lattice system, for example, for all n, and for all k, you know the value at L equals 0. And you start from there. I always do you have no way to easily to calculate for the large L, like means you involve with time. And very often I came up with a difficulty because the algorithm is not linear, it's not explicit. So you have to solve nonlinear system. So do you have any comments for this kind of,
I think these two algorithms are from different topics. I mean, since maybe 1 + 1 dimensional, in your case maybe simpler, but in 1 + 1 case, in my case, is very complicated. I mean, the reduction method in this one is very difficult.
I have the same difficulty. After the reduction, usually the system becomes more difficult to deal with. Yeah, the same. Yeah. Mm-hmm.
Okay, so sorry, I don't have a very quick comment for me for you now. Yeah. I will communicate with you maybe after this.
Yeah, later on. Yes. Okay. Thank you. Very good. Very interesting talk.
Yeah. Thanks for your comments and questions. Yes.
Thank you. Is there any other questions or comments?
Can I ask a question?
Please.
Yes.
It's very naive questions. You know, there are cube determinant. There are cube determinant. Are there cube Pfaffian?
What do you mean by cube determinant?
Cube determinant means you know, the determinant matrix is a defined on plane. You can say that. You can say that.
Yeah.
And then you will have a cube.
Okay.
First you have a cube matrix. Okay.
I don't know any cube determinant. Sorry for that.
Yeah, because sometimes the cube determinant can generate integral systems also.
Okay, so what type of integrable system related to the cube determinant?
Let me say that. I remember there is a paper by James Atkinson, and he has he has a result on fully discrete systems derived from cube determinant.
Okay, I'm sorry that I don't know any results about the so sorry for that. but it's very interesting to see whether we can design a condensation.
So I mean you can right? you can generalize the Euro determinant to the cube case.
Yes.
And then the Pfaffian can also should be generalized to the cube case.
Yes. That's correct. Thanks for your comments. Yes, it's very interesting.
Okay. Other questions or comments?
Maybe I've got
yes.
a question. So because this is another thing, right? Like maybe a comment, maybe not a complete answer, but because all these algorithms involving determinants and all these algorithms involving acceleration of computations of determinants are integrable, also because in some sense their computational complexity is polynomial. Do you have any hint on the computational complexity of your algorithms?
Yes. So I did some, I mean, I wrote a MATLAB program, I say that. So I did a very little computing complexity for the program. So it's of the four times. I mean, oops.
So it's n to the
sort of
fourth.
Four times, yes.
I see.
Or 4 times. So this one is larger than the skew LU decomposition. I mean, from the skew LU decomposition, it's only need an n cube.
Yeah.
Here and fourth time. So in some sense, it's not a very good algorithm, but I hope we can find some future application in combinatorics or some other topics, rather than the algorithm. So yes, I mentioned here. I just want to maybe here we will do something related to the combinatorics. Yes.
Thank you.
Yes, thanks for your comments.
Okay, other questions or comments? If there's no, so let's thank speaker again. So
yeah,
thank you very much.
Yeah. Thank you.
Bye.
I will stop sharing, right?
Yeah, you can stop sharing. Thank you for your talk. And
thank you very much, Shi-Hao. Nice to see you. Thank you.
Yeah, nice to see you.
Bye-bye.
Yeah, bye-bye.
So just a quick announcement. So the next talk will be on April the 22nd, this time at 12 p.m. So it's on
10
still
o'clock
on
in Beijing time.
Yeah, exactly. Okay, thank you so much for everybody for attending this very interesting talk, and see you next time. Bye.
See you.
See you.
Bye.
See you.
Bye.
See you. Bye.